Welcome back to Echoes of Skunk Works, the channel that pulls back the black curtain on the classified projects, the radical ideas, and the unsung innovators who gave America its technological edge. In the high-stakes game of aerial warfare, detection is death. For decades, radar was the undisputed king, the all-seeing eye that stripped the sky of its hiding places. Nations poured billions into building faster, higher-flying aircraft, more powerful radars, and longer-ranged missiles, a relentless cycle of measure and countermeasure. But what if the answer wasn't just to fly faster or higher? What if the answer was to disappear? The concept of stealth, of making an aircraft invisible to radar, seems like modern magic, born from supercomputers and exotic materials. But the seed of that revolution, the fundamental breakthrough, didn't come from a boardroom or a university lab. It came from a workbench. It came from a technician, a hands-on guy, who saw something incredibly simple that all the brilliant physicists and aerodynamicists were overlooking. His idea wasn't based on complex equations. It was based on high school geometry and a spool of wire. It was mocked. It was dismissed as naive, as crazy, as a fundamental misunderstanding of radar physics. His boss told him to stick to fixing scopes. But that crazy wire trick, it unlocked the secret. It became the cornerstone of a technology that rendered billions in enemy air defenses obsolete and changed the very nature of air power forever. This is how one technician's crazy wire trick made U.S. jets invisible to radar. Before we delve into the classified files, if you believe that groundbreaking ideas often come from unexpected sources and that challenging conventional wisdom is crucial, then I need you to secure our signal. First, subscribe to the channel and activate the notification bell. It's your clearance for all future intelligence briefings. Second, give this video a like. It helps amplify our signal across the network. And finally, drop a comment below. Let us know what country and city you're receiving this transmission from. Our global network of aviation and technology enthusiasts is vital to our mission. All right, let's power up the radar range. My name is Leo Kachmar, and back in 1974, my world was measured in decibels and microwave frequencies. I wasn't an aerodynamicist designing sleek wings, nor a physicist calculating quantum interactions. I was an electronics technician, grade the third, working deep inside the classified confines of Lockheed's Advanced Development Projects, the legendary Skunk Works out in Burbank, California. My official job title involved something long and boring about radar cross-section measurement and analysis support. Unofficially, I was a glorified range monkey. My days were spent in the scorching Mojave Desert heat at our remote radar test facility, Area 5, a desolate patch of scrubland miles from anywhere, dominated by the massive steerable dishes of our radar arrays and the pylons where we mounted test shapes and aircraft models. My job was to calibrate the sensitive receivers, troubleshoot the finicky transmitters, align the antennas, and meticulously record the raw data as microwaves bounced off whatever shape the real engineers wanted to test that day. We were chasing the Holy Grail, low observables, or stealth. The Vietnam War had been a brutal wake-up call. Our sophisticated fighters and bombers, bristling with electronics, were being shot down in alarming numbers by relatively simple Soviet-supplied surface-to-air missiles, SAMs, guided by radar. Flying faster or higher wasn't enough anymore. We had to become harder to see. The Skunk Works, under the legendary Kelly Johnson and his brilliant successor, Ben Rich, was at the forefront of this secret war, exploring radical new aircraft shapes, radar-absorbent materials, RAM, and electronic countermeasures. It was heady stuff, the absolute cutting edge. And I was the guy tightening the coaxial connectors and swapping out burnt-out klystron tubes. The prevailing wisdom in RCS reduction back then was a combination of two main approaches. First, shaping. Aerodynamicists knew that smooth curved surfaces, like those on conventional aircraft, tended to scatter radar waves in many directions, but also had unavoidable specular reflections, bright mirror-like glints that flashed back towards the radar source, especially from perpendicular surfaces like engine inlets, tail fins, or fuselage sides. The goal was to minimize these perpendicular surfaces, use complex curves, blend wings into fuselages, basically make the plane look like a futuristic organic sculpture. Think of the SR-71 Blackbird, another Skunk Works marvel. All smooth curves, blended shapes, tilted fins. It had a significantly lower RCS than a conventional bomber, but it was still far from invisible, especially to lower frequency radars. The second approach was materials. RAM, exotic paints and composite structures designed to absorb microwave energy, turning the radar pulse into heat instead of reflecting it. We were testing early versions of iron ball paint and ferrite-loaded composites. They worked, sort of. They were heavy, expensive, fragile, difficult to maintain, and only really effective against specific radar frequencies. The real engineers, the PhDs in fluid dynamics and materials science who would breeze onto the range in their air-conditioned cars, run their tests, and disappear back to Burbank, were focused on refining these two approaches. They were building complex, computer-modeled shapes with compound curves. They were experimenting with multi-layered RAM coatings. They were chasing incremental improvements, shaving decibels off the RCS through brute force computation and exotic chemistry. And I was the guy standing out on the pylon platform, getting bombarded by microwaves. We didn't worry so much about safety back then. Physically mounting their beautiful, complex, and often disappointing test models. I wasn't an engineer, not formally. I'd done 2 years of electronics tech school after a stint in the Navy fixing shipboard radars. But I was good with my hands, and I had an intuitive feel for how electromagnetic waves behaved. Fixing radars day in and day out, you develop a sixth sense for how signals bounce, how they interfere, how they reflect off different shapes and materials. And the more I watched these tests, the more I listened to the engineers argue about boundary layer effects and dielectric constants, the more I felt like they were missing something. Something simple, something fundamental. They were obsessed with smooth curves, scattering energy in all directions, hoping enough would dissipate. They were trying to absorb the energy with RAM. But what if you didn't scatter it randomly? What if you didn't try to absorb it? What if you controlled where the reflection went? What if you deliberately designed the shape so that the inevitable reflections were channeled away, concentrated into just a few, very narrow beams, pointed away from the radar source? Think of a diamond. It has flat facets. When light hits it, it doesn't just scatter fuzzily, it reflects in brilliant, sharp flashes, but only in specific directions. In between those directions, it's relatively dark. What if you designed an airplane like a poorly cut diamond, with flat panels, angled just right, so that the radar reflections were concentrated into narrow spikes, shooting off harmlessly into space, leaving almost no energy returning to the radar receiver? It seemed childishly simple. High school physics. Angle of incidence equals angle of reflection. Why were these brilliant men, with their supercomputers and their million-dollar budgets, seemingly ignoring it? I started sketching, not on official engineering pads, but on the back of data log sheets during long, boring calibration runs. I drew simple shapes, cubes, pyramids, faceted spheres. I drew lines representing incoming radar waves and calculated the reflection angles. It was undeniable. Flat panels, carefully angled, could direct the vast majority of the reflected energy away from the source. Curves, paradoxically, scattered energy more broadly, making them more likely to send some energy back in all directions, including towards the radar. But planes needed to be aerodynamic, right? They needed smooth, curved wings to generate lift efficiently. You couldn't just build a flying box. Or could you? What if the entire shape was made of flat panels? Triangular facets, perhaps. Like a low-polygon computer model before the smoothing algorithms kicked in. It would be an aerodynamic nightmare at low speeds, unstable, maybe even uncontrollable. But at high speeds, maybe the sharp edges, the flat planes, wouldn't be as catastrophic as conventional wisdom suggested. Maybe the RCS reduction benefits would outweigh the aerodynamic penalties. It was a crazy thought, flying in the face of 50 years of aircraft design. But the radar physics seemed undeniable. I needed to test it. I couldn't requisition official model shop time for my flying geometry project. But the range technicians, my buddies, we had downtime. We had scrap materials. We had access to the machine shop after hours. And we had wire. Spools and spools of copper and steel wire, used for antenna repairs, grounding straps, and makeshift fixes. Wire was easy to bend, easy to shape. What if I built my models not out of solid material but as simple wireframes, just outlining the edges of the faceted shapes? Radar waves interact most strongly with sharp edges and discontinuities. A wireframe representing the critical edge geometry might give me a rough but indicative RCS measurement. It was a crude approximation, a technician's shortcut, but it was fast and cheap. My first model was pathetic. A simple pyramid, about 2 feet tall, made of brazed copper wire, mounted on a wooden pole. I put it on the test pylon during a lunch break, when the official test was paused. I aligned the radar, our high-frequency X-band tracking radar, directly at one of the flat, triangular wireframe faces. I powered up the transmitter for just a few seconds, praying I wouldn't fry the receiver or trigger any alarms. I watched the raw return signal strength on my oscilloscope. It was low, astonishingly low, almost down in the noise floor. Then I rotated the pylon slightly, just a few degrees, so the radar was hitting the edge between two facets. The signal on the scope exploded, a massive spike, orders of magnitude stronger than the reflection from the flat face. It was exactly as I'd predicted. The flat panels were reflecting the energy away harmlessly. The edges were scattering brightly, but only in specific narrow angles. A wireframe pyramid was, effectively, almost invisible head-on. My heart was pounding. This wasn't just theory anymore. This was data. Crude, unofficial, probably inaccurate data, but data. I started building more complex wireframe shapes, faceted diamonds, shapes with sharp, angled edges, deliberately avoiding curves. I even built a crude angular delta-wing aircraft shape, purely out of wire, focusing on aligning the leading and trailing edges so their reflections would spike in the same, predictable directions. Each time, the results were the same. Incredibly low RCS readings when viewed face-on to a panel, massive spikes when viewed edge-on. I was onto something huge, something that contradicted everything the real engineers were doing. I knew I had to tell someone. I couldn't keep running illicit tests during lunch breaks. I needed real resources, real analysis. I requested a meeting with my immediate supervisor, Dr. Alan Thornton, the head of the RCS measurement group. Thornton was a sharp guy, a physicist by training, younger than Ainsworth types, more open to new ideas, but still very much part of the established system. He was also perpetually overworked, stressed, and under pressure from the Chimera team and Ben Rich himself to produce results. I rehearsed my pitch. I wouldn't lead with the crazy wireframe results. I'd start with the basic physics, the angle of incidence reflection, the limitations of curved surfaces, the potential benefits of faceting. I'd present it as a theoretical exploration, a possible avenue for supplemental RCS reduction. I wouldn't mention my unauthorized tests. I'd just plant the seed. The meeting was a disaster. Thornton listened patiently for about 5 minutes, tapping his pen, his eyes glazing over as I sketched reflection angles on his whiteboard. Then he held up a hand, stopping me mid-sentence. "Kachmar," he sighed, sounding infinitely weary. "I appreciate the enthusiasm, the outside-the-box thinking. But we've been over this. Basic radar theory. Smooth blended shapes minimize specular returns. Facets, flat panels. You're intentionally creating specular surfaces. Yes, you might direct the reflection away at one specific angle, but from every other angle you're creating a perfect mirror. And edges. Good God, man. Diffraction from sharp edges is a primary source of radar return. Your wireframe models, somehow he knew about them. The grapevine worked both ways. They're proving the opposite of what you think. Those massive spikes you're seeing off the edges? That's why we avoid sharp edges. That's why we blend and curve. I tried to argue. But sir, if you align the edges, if you limit the number of edge orientations, align the edges? He actually chuckled, a dry, humorless sound. Kachmar, we're building airplanes, not origami. Airplanes need to turn, to bank, to maneuver. Those edge spikes will flash like strobe lights from every angle except the one precise angle you designed for. And the aerodynamics, a faceted airplane, it would fly like a brick. Kelly Johnson would have a heart attack. He stood up, signaling the meeting was over. Look, Leo, he said, his tone softening slightly, becoming almost paternal. It's a cute idea. It shows initiative, but it's fundamentally naive. It ignores the complexities of multi-frequency radar, of polarization, of aerodynamic necessity. It's a dead end, a distraction. We have multi-million-dollar computer simulations, run by PhDs in computational electromagnetics, telling us that smooth curves and RAM are the path forward. You have a spool of copper wire in a high school geometry textbook. He put a hand on my shoulder. Stick to the oscilloscopes, kid. Keep the range running. That's your job. That's where you contribute. Leave the crazy ideas to the guys who actually understand the physics. He walked me to the door. Seriously, Leo, drop it, for your own good. Pursuing this, it'll make you look like a joke. It'll kill your career here before it even starts. He called it crazy. He called me naive. He told me to stick to my job. He threatened my career. He couldn't have lit a bigger fire under me if he'd used a flamethrower. Dr. Thornton's dismissal was intended as a final nail in the coffin of my crazy idea. He'd wielded the full weight of his authority, the consensus of the PhDs, the threat to my nascent career. He expected me to fold, to retreat back to my oscilloscopes, chastened and compliant. What he didn't understand, what none of the brilliant men in their clean offices seemed to grasp, was the fundamental difference between an academic exercise and a conviction born from observation. They saw equations. I saw the raw signal dancing on my scope. They saw elegant theories of aerodynamic flow. I saw microwaves bouncing off metal. Their world was smooth curves and incremental gains. My world, the technician's world, was about finding the simple, often ugly truth of how things actually worked, even if it defied the textbook. His laughter wasn't a deterrent. It was gasoline on the fire. It confirmed everything I suspected about the disconnect between the theoretical priesthood and the practical realities we grappled with on the range every day. They were so invested in their complex, multi-million-dollar path, the path of exotic RAM and computationally derived curves, that they were blind to a potentially simpler, more fundamental solution staring them in the face. Copper wire and a high school geometry textbook. He meant it as an insult. I took it as a badge of honor. Because my wire and geometry had just shown me something their supercomputers hadn't. My resolve hardened. Official channels were closed. My boss had explicitly forbidden further work. Fine. If I couldn't work within the system, I'd work outside it. My late-night wireframe tests were suggestive, tantalizing, but Thornton was right about one thing. They were crude. A wireframe only represents the edges. It doesn't fully capture the behavior of the flat surfaces, the potential for internal reflections, the interaction between facets. I needed something better. I needed a solid model, something built with precision, something that represented the actual faceted geometry I envisioned, something that would yield data so clear, so undeniable, that even Thornton, even Ben Rich himself, couldn't ignore it. But how? The Skunk Works model shop was Fort Knox, reserved for official projects blessed by Kelly Johnson or Ben Rich. Requesting time to build my flying diamond was unthinkable. Materials requisition. Impossible. I was back to square one, a technician with a radical idea and zero resources. Except, I wasn't entirely alone. I had the range technicians, my fellow range monkeys, guys who spent their days getting irradiated alongside me, guys who shared my skepticism towards the front office pronouncements. And I had Mac. McGregor Mac Davies was the lead machinist in the experimental fabrication shop, a gruff, heavily tattooed Scotsman who had served in the Royal Air Force during the Blitz and possessed a profound distrust of anyone with a degree and clean fingernails. He was an artist with metal, capable of coaxing tolerances measured in microns from machines older than I was. More importantly, he hated waste. He saw the beautiful, complex, but ultimately ineffective shapes the PhDs designed, saw the millions spent on exotic materials and complex tooling, and he'd just shake his head and mutter about academic bloody nonsense. I found Mac in his kingdom, a vast, noisy cavern filled with lathes, mills, and the sharp metallic smell of cutting oil. He was arguing loudly and profanely with a young, terrified-looking engineer about the impossibility of achieving a specified tolerance on a turbine blade mock-up. I waited until the engineer retreated, pale and defeated. "Mac," I began cautiously. "Thornton kick your ass back to the miners, Kachmar?" Mac grunted, not looking up from the blueprint he was now glaring at. News traveled fast. "Something like that," I admitted. "Called my idea crazy." "Probably is," Mac retorted. "Most ideas cooked up by you lab coats are crazy. What was it this time? Square wings?" "Flat panels," I corrected. "Faceted fuselage, like a diamond." Mac finally looked up, a flicker of interest behind his usual scowl. "Flat panels? Instead of them fancy bloody curves?" "Yeah, to control the radar reflection. Angle of incidence equals angle of reflection. Basic stuff. But Thornton says it's naive, ignores the edge diffraction." Mac snorted. "Thornton couldn't machine his way out of a paper bag. Thinks metal just appears in the shape he draws it. Flat panels, eh?" He actually seemed intrigued. "Easier to make, I'll give you that. No compound bloody curves to tool up for. But fly? Sounds like a brick." "Maybe," I conceded. "But the radar return." "Mac, I ran some rough tests. Wireframes. It was low, really low, head on." Mac was silent for a moment, wiping his hands on an impossibly dirty rag. "Wireframes don't mean squat, kid. You need a solid model. Precision angles. See how the surfaces really bounce the signal." "I know," I said, the frustration returning. "But I can't get shop time. It's not an official project. Thornton specifically forbade it." Mac looked around his shop, at the massive humming machines, the racks of raw aluminum and steel stock. A slow, conspiratorial grin spread across his face. "Official shop time," he said. "Ends at 1700. My time. Starts whenever the hell I say it does." He winked. "Got some personal projects I work on after hours. Always need an extra pair of hands, especially hands that know which end of a micrometer is which. Unlike that bloody idiot who was just in here." He looked me up and down. "You afraid of getting your hands dirty, Kachmar?" Mac became my secret weapon, my Michelangelo, for the next 2 months. Warehouse 7, my electronics hideout, and Mac's fabrication shop became the twin poles of my clandestine existence. By day, I was Leo Kachmar, the dutiful, ignored radar tech. By night, I was part of Mac's ghost crew, learning the brutal, beautiful art of shaping metal. We didn't build it out of aluminum. Too expensive, too difficult to machine precisely without raising flags. Mac found a stash of high-density modeling foam and, more importantly, thin sheets of aircraft-grade plywood coated with adhesive copper foil, materials used for creating mock-ups and checking antenna patterns. Perfect. Lightweight, easy to shape, and the copper foil would provide a realistic radar reflective surface. Mac was a wizard. Using my sketches and the crude calculations I'd refined, he programmed one of the older, manually controlled milling machines, one less likely to have its usage logs scrutinized, and began carving the facets. It was a painstaking process. Every angle had to be perfect. Every edge had to be sharp. Unlike the smooth, forgiving curves the other engineers favored, my faceted design was brutally unforgiving. A tiny error in one angle would throw off the entire reflection pattern. We worked in hushed tones, under dim lights, the whine of the mill echoing in the deserted shop, constantly listening for the footsteps of the night watchman or, worse, Thornton making a surprise late-night visit. We covered the machine and our work-in-progress model with greasy tarps whenever we heard someone approaching. It was nerve-wracking, exhilarating, and utterly exhausting. While Mac shaped the physical form, I plunged deeper into the why. Thornton's dismissal had stung, but his points about edge diffraction weren't entirely wrong. Why did my wireframes show such low returns from the flat faces, despite the obvious edge effects? Simple geometry wasn't enough. I needed real physics. My salvation came, ironically, from the enemy. Sully was the electronics tech in the previous story. Mac is the machinist here, correcting internal monologue. Mac had a friend, another old RAF veteran working in the technical library, who occasionally got his hands on obscure, translated Soviet technical journals. In one of them, a dense, almost incomprehensible paper by a Russian mathematician named Pyotr Ufimtsev, I found it. Ufimtsev's Physical Theory of Diffraction, PTD. It was revolutionary. While Western radar theory focused heavily on specular reflections from surfaces, Ufimtsev had developed complex equations that accurately predicted the radar returns generated by edges and discontinuities. His math showed that while edges did produce strong returns, these returns were concentrated in specific, predictable directions based on the edge's geometry and orientation relative to the radar. And, crucially, his theory also implicitly confirmed what my wireframe tests suggested. Away from those specific edge reflection angles, the return from a flat, angled plate could be incredibly, vanishingly low. Ufimtsev's work wasn't about eliminating reflections. It was about predicting and controlling them. It was the theoretical backbone my intuitive concept desperately needed. I felt like I had found the Dead Sea Scrolls of stealth. Armed with Ufimtsev's equations, or at least my rudimentary understanding of them, I started refining the model's shape. It wasn't just about flat panels anymore. It was about edge alignment. I realized that if I could design the shape so that the major edges, the wing leading edges, the tail edges, the fuselage chines, were all aligned along just a few common angles, then the strong edge reflections would be concentrated into just a few, narrow spikes on the radar display. If you could keep the radar source out of those spike directions, the aircraft would remain effectively invisible. This led to the radical, angular, almost crystalline shapes that would later define stealth aircraft. Sharp angles, sawtooth panel edges, designed to scatter edge reflections, parallel alignment of leading and trailing edges, shapes that looked completely non-aerodynamic, utterly alien. Mac, translating my increasingly bizarre sketches into physical reality, just shook his head. "Looks like a bloody cubist nightmare, Kachmar," he'd grumble. "You sure this thing's supposed to fly?" "It doesn't have to fly, Mac," I reminded him. "It just has to disappear." We nicknamed the finished model Echo. It was about 4 feet long, made of copper foil-covered plywood, faceted like a rough-cut gem. It had sharp, swept wings, canted V-tails, and brutal, angular fuselage chines. It looked like nothing that had ever flown before. It was angular, menacing, and utterly devoid of curves. It was beautiful. And it was ready. Now, the final hurdle, getting it onto the radar range. Thornton monitored the official test schedule like a hawk. Slipping Echo onto the pylon during a scheduled run was impossible. We needed dedicated time. We needed the high-power, multi-frequency radars. We needed the sensitive, calibrated receivers. We needed the official range, not my lunch break hacks. Mac, again, was the key. He discovered that a calibration test was scheduled for the upcoming weekend, a normally off-limits time. The range needed to precisely measure the background clutter and reflectivity of the pylon and the surrounding desert to ensure the accuracy of future tests. They used standard calibration shapes: spheres, cylinders, corner reflectors. Mac knew the chief range officer, another old NCO who owed him for years of keeping the pylon rotation motors running. "Got a new calibration target we need to check, Tom," Mac told him, his voice casual. "Experimental design. Supposed to have a really low, stable return. Perfect for checking receiver sensitivity." He showed the CRO a deliberately vague schematic, emphasizing the flat panels and stable mounting points, omitting any mention of stealth or faceted geometry. The CRO, busy and trusting Mac, just shrugged. "Sunday morning, RO 600, before the sun gets too high and messes with the thermals. You get 2 hours. Don't break anything." We had our window. Sunday morning, 2 hours. One chance to put Echo under the all-seeing eye of the Skunk Works' most powerful radars, right under Thornton's nose. As Mac and I carefully wrapped Echo in canvas tarps, preparing to transport it out to Area 5 under the cover of pre-dawn darkness, the weight of the moment hit me. This was it. Everything. My career, Mac's neck, the entire future of stealth as I envisioned it, rested on this ugly copper-foiled model, on Ufimtsev's obscure equations, and on the simple physics of angle of incidence equals angle of reflection. Thornton had called my wire trick crazy. He was about to find out just how crazy it really was. The pre-dawn chill of the Mojave Desert felt colder, sharper, somehow more significant on that Sunday morning. We worked in near silence under the harsh glare of temporary floodlights, Mac and I carefully mounting Echo onto the test pylon at Area 5. The range was deserted, eerily quiet except for the low hum of the generators and the distant cry of a coyote. Every clink of metal, every scrape of the model against the mounting bracket sounded like a thunderclap, announcing our illicit activities to the entire sleeping base. Mac moved with the practiced, deliberate calm of a master craftsman, ensuring every alignment bolt was tight, every angle precise. I nervously double-checked the connections to the pylon's remote rotation controls, my hands clumsy with a mixture of fatigue, fear, and a bone-deep, gut-wrenching anticipation. Was Thornton right? Would the flat panels act like mirrors, creating massive, uncontrollable flashes? Would the edge diffraction effects dominate, making the model brighter than a conventional shape? Or would Ufimtsev's arcane mathematics, my wireframe intuition, and Mac's meticulous craftsmanship actually hold true? In the control bunker, 50 yards away, buried under tons of earth and concrete, the atmosphere was thick enough to cut with a knife. Chief Range Officer Tom Riley, bleary-eyed and sipping coffee, sat at the main console, ready to run the standard calibration sweeps. He still thought Echo was just an unusually shaped calibration target. Beside him, I huddled over a secondary display, a high-resolution plan position indicator, PPI scope, and an A-scope, amplitude versus range, my heart hammering against my ribs. Mac stood behind me, arms crossed, his face an unreadable mask, but his knuckles were white where he gripped the back of my chair. "All right, Kachmar." Riley grunted, flipping switches. "Powering up the X-band. Standard sweep pattern, 30 degrees left to right, 0 elevation. Let's see what your stable target looks like." The radar transmitter hummed to life, a sound I knew intimately, the pulse repetition frequency a steady, familiar beat. On the PPI scope, the sweeping green line painted the background clutter, the desert floor, the distant mountains. As the beam crossed the pylon's position, nothing. Just the faintest, almost imperceptible blip, barely distinguishable from the background noise. My breath caught. It was low, lower than the pylon itself should have been. "Huh," Riley muttered, peering closer at his screen. "Receiver sensitivity must be off again. Signal's way down." He reached for the gain control. "Don't touch that," I yelped, startling him. "Sir, please, just complete the sweep." Riley gave me a strange look but shrugged. The beam continued its sweep. Still nothing. Just that ghostly, near-invisible return when the radar was pointed directly at one of Echo's flat, precisely angled facets. But then, as the beam hit the edge of the model, the edge between two panels, flash. A brilliant, searing spike erupted on the A-scope, momentarily saturating the receiver. The PPI scope showed a bright, sharp line painting right at the edge angle. "Whoa!" Riley exclaimed. "What the hell was that? Loose connection on your model, Kachmar. That's not stable." "No, sir," I said, my voice trembling, not with fear, but with triumph. That's the edge diffraction. It's doing exactly what it's supposed to." Mac's hand gripped my shoulder, hard. He saw it too. "Run it again," I urged Riley. "But this time, step through, 1 degree at a time. Hold on the angles where the return disappears." Skeptically, Riley complied. He stepped the powerful radar beam across the model's forward sector. Angle after angle showed nothing. Just noise. The model, head-on, was effectively invisible, swallowed by the desert clutter. Then, as he hit the precise angle corresponding to the alignment of the leading wing edges, flash, another massive spike. He moved 1 degree further. Gone. Back to noise. He continued the sweep. Nothing. Nothing, until he hit the angle corresponding to the canted tail fins. Flash. Another spike. Exactly where Ufimtsev's equations and my simple sketches predicted it would be. It was undeniable. Echo wasn't just reflecting the radar, it was channeling it. It was concentrating almost all the reflected energy into a few narrow, predictable beams, leaving vast angular zones where the return signal was practically zero. It wasn't just low observable, it was selectively invisible. Mac let out a long, slow whistle. "Well, I'll be damned, kid," he whispered, his voice filled with awe. "Your crazy diamond. It actually disappears." We spent the next hour frantically gathering data, running sweeps with different radar frequencies, different polarizations. The results held. Lower frequency S-band radar showed a slightly larger return, as expected, but the fundamental principle remained. Massive reduction head-on, predictable spikes off-angle. My crazy wire trick, translated into solid faceted geometry, worked. It worked better than any RAM, better than any smooth blended shape had ever achieved on this range. As our 2 hours ran out, as the sun climbed higher, signaling the end of our clandestine test, I knew we had captured lightning in a bottle. We had the proof, hard, irrefutable, classified proof. Mac, sensing the shift, looked at Riley. "Tom," he said, his voice casual but firm, "this data, it's sensitive. Project calibration files. Needs to be logged under special access." Riley, finally understanding that this was no ordinary calibration target, just nodded slowly, his eyes wide. "Yeah, Mac, got it. Special access." The official log would show a routine calibration run, but the real data, saved onto magnetic tape, locked in my briefcase, was a ticking time bomb under the established orthodoxy of stealth design. Presenting the data, even with its undeniable implications, was still fraught with risk. But now I wasn't just a junior tech with a theory. I had results, verified results from their own range, their own equipment. And Mac Davies, a man whose practical expertise was legendary, was my witness, my ally. We didn't go to Thornton. We went straight to Ben Rich, Kelly Johnson's successor, the pragmatic genius who was already exploring unconventional ideas. The meeting was short, intense. Rich, flanked by his top engineers, pointedly. Thornton was not invited, listened silently as I presented the data, the graphs, the physics, Ufimtsev's equations. I didn't gloat. I didn't say, "I told you so." I just laid out the facts. When I finished, Rich leaned back, tenting his fingers, a thoughtful, calculating expression on his face. "Facets," he mused. "Edge alignment. Physical theory of diffraction." He looked at Mac. "You built this, Mac?" Mac nodded. Kid had the brains. I just bent the metal, well, the plywood. Rich looked back at me. "Thornton called this crazy." "Yes, sir," I confirmed. "He also said it was impossible." Rich allowed himself a small, rare smile. "Well, Mr. Kachmar," he said, tapping the data printout, "it seems you have achieved the impossible." That meeting, fueled by the data from our illicit Sunday morning test, changed everything. The Skunk Works officially, secretly, pivoted. The focus shifted almost overnight, from complex curves and RAM to faceted, edge-aligned geometries. My crazy wire trick, Ufimtsev's obscure mathematics, and Mac's fabrication skills became the foundation for Project Harvey, the code name for the Have-Blue prototype, the direct precursor to the F-117 Nighthawk, the world's first operational stealth aircraft. The angular, alien, unflyable shape of the Nighthawk, the shape that baffled the world when it was finally revealed, was a direct descendant of Echo, my copper-foiled plywood model. My name never appeared on the patents. I remained, officially, just a technician who got lucky. But those of us who were there, who saw the data from Area 5 that Sunday morning, we knew. We knew that the multi-billion-dollar revolution in air power, the era of stealth that rendered enemy radars virtually obsolete, hadn't started in a supercomputer. It had started with a spool of wire, a dismissed technician, and a crazy idea that refused to die. They called it a joke. Now, it was the invisible shield of the nation,